Hello everyone, we are group 14, otherwise known as XYZ, and for our final project this semester in EC311, we made the XYZ23 microprocessor. So this is a custom single cycle microprocessor that has its own assembly language and assembler and communicates to the FPGA via UART protocol. So yeah, let's begin. Alright, so before getting into the code of our assembler, I wanted to first show the instruction set that we're using. So this is heavily influenced by the EC311 simplified Intel assembly instruction set, where we have a bunch of moving in and out of registers and memory. We have a bunch of ALU functions such as the add, subtract, increment, and or XOR. And then we also have comparison and jump operators that allow for for loops within our microprocessor. Alright, so I'm going to go a little bit into the code now. So what we see on the screen is a snippet that I'll explain in a second, but overall the function of the code is to accept a .xyz file that is a file containing the assembly language with the instruction set provided on the previous screen. And what the code does, it essentially turns it into a binary instruction set that our ALU will be able to understand. So here's just a little snippet of the code, and this part of the code pretty much takes in a line of instruction, and if it sees that the instruction label is move, it'll determine which of the parameters are the acceptable parameters, and this way we could tell the ALU whether we're speaking between registers and memory, memory and registers, registers and registers, or registers and numbers. One nice feature of our assembler, which can be seen also in the previous slide, is we have a syntax error detection system that will provide the user with feedback on the lines at which there may have been syntax errors that prevented the program from being assembled correctly. So here's just an example of how we might use our assembler to assemble a program. So on the left we have a fib.xyz file that contains a Fibonacci sequence problem in our XYZ assembly language. After that's written, we use the assembler to create the .bin file, essentially just passing the XYZ file as a parameter, and we end up with a .bin file of binary, which can easily be interpreted by the FPGA and the ALU on it. While on the topic of the C++ portion of this code, I think it's important to bring up the memory dump. That is essentially the returned values from the FPGA after the microprocessor is done processing. And essentially what we do is we grab all that data, we split it into separate memory cells, and create essentially a table of values in decimal that the user is able to interpret more easily than the binary that the FPGA has. Here's just a small example of what that table might look like.
So for our example, to exemplify the use of the MPU, we did the Fibonacci series. So we found the sum, we input sum number 4, let's say, and we find the sum of the Fibonacci numbers that precede it. So in this case, you'd expect the sum to be 1 plus 1 plus 2 plus 3, which makes 6. So the output should ultimately be 6, which you will see later on in the video. So all of our code is written in the XYZ language, which is a standard assembly language that Thomas talked about before. Just wanted to point out here, you see the common input parameters where you have the actual opcode, right? Whether it be move, decrement, add, compare. Then you've got the first parameter, which is typically the register here, and the second parameter, which is either a register or a number. You might note that there's some instructions like jump if not equal, halt, or registrings, which only have 1 or 2 sections. The other ones are just left blank, so in this case, when we say blank, we just mean all zeros. So to actually get this into a format that the FPGA can read, we need to use binary. So in this case, we have to use an assembler, which is all written in C++, as Thomas described before. And the output of this is a binary file. Now we've laid this out nicely so that you can see that there's 10 different rows here. Each row is made up of 24 bits, as we talked about before, right? There's 8 bits in each parameter. 3 parameters make up an instruction, and these here are 10 instructions. Now to actually get these into FPGA, we have to use the UART protocol, which is something that I spent quite a bit of time on, but was unable to get working. The biggest issue for us was implementing a file transfer protocol. One big one that we looked into was the current protocol, but we were unable to get the FPGA to read in the data. So we'd be able to get in 8 bits of data, sometimes even 16 bits of data, but to get the full 24-bit instruction was for some reason not working for us. Anywho, we decided just to show off 8 bits at a time. So this is all code from the FPGA dude adapted to fit with our code. So you can see here we just input 8 bits. This is the actual code that we used. We didn't use a test bench. We were more so used a quote-unquote test bench source because it's hard to use TX and RX. You can't really do that with a test bench. So instead we use this provided UART test. And you can see here that we input the values, and then the buffer wasn't fully flushed, but you can see that it does output values that were read into it. And you'll see in the next case when we just put all zeros, it actually does read all of those zeros in, and then copy those and throw those into MOBA Xterm, which is just our serial emulator, our terminal emulator, and voila, we have all of those 8 zeros perfectly in there.
Next, I will be going over the Verilog code for our microprocessor. Here you can see our module with all its inputs and outputs. Going further down here, you'll see that we first declare registers and memory along with every other variable. And then down here, we have all our opcodes for the different operations that we mentioned before. Further down here, we have our always statement, or always one of the always blocks, which detects for a negative edge of the clock, and it will get the instruction that was stored in the memory, which I'll go on about a little further here. So down here we have our main always block, which detects for a positive edge of the clock, a reset, or an instruction input before beginning. In this area we have our write block, which writes the instruction inputs to parts of the memory, and then we increase the pointer counter by 1 every time it does so. And once it detects a halt, we change the halt detection to a 1 and also reset the PC back to 0 so that it can execute all the operations. And here we have a reset block that just initializes everything. It sets all the variables to 0, like pointer counter, the comparison result, halt detection, stuff like that, and also initializes the memory and registers. Down here we have our execute block that begins once a halt has been detected. As I mentioned before, once a halt is detected, the instructions stop getting written to the memory and instead start to operate. So down here you'll see all our cases for all the operations that we mentioned before, and they all just happen after all the instructions have been loaded.
So here is our test bench for our microprocessor. This one is our implementation of our microprocessor module. We have a clock, we have a reset, we have an instruction input, we have a select memory, and we have an output memory. We also have a program down flag. So here in the clock cycle, we will receive instruction from as input. And for our select memory, this one is our memory address, which should be output. And since we're doing the Fibonacci, we calculate our answer will be output at address 40. That's why we pick the select memory at 40. And this binary code is our assembly code for the Fibonacci. Next is our waveform. So in the waveform here, as you can see, the instruction will not be loaded until all the instructions are stored in the memory. So it keep showing X, keep X. Here, once we reach the halt, which is stop everything, the instruction will be loaded one by one and do the calculation. And here we do it faster and keep doing the calculation. So in our Fibonacci, we literally will get an answer which is 1 plus 2 plus 3. We'll get answer 6. And since we're doing the jump, the Fibonacci will compare the register first. And then since the registers now are not equal, then we jump back and do the calculation again. So through the cycle, finally we can get an answer which is 6. Just a little bit. Okay, here we get our answer at 6, which means our program finished and is successful.